Good evening. My name is Richard Thompson, and I'm going to be going over cryptography and cybersecurity. So, what is cryptography? To simply put it, it means to scramble your information in an organized way. That way it can be unscrambled and translated. So, let's say you have something you want to encrypt. This can be a message or pretty much anything with computers because of the way that computers translate everything into code. So you take your message and apply what's called a cipher key. You can share this key with the person that your information is intended for, and they can use that key to unscramble your message. So keys are done one of two ways. Shared key encryption is a little more old school, so you have a key and you give a copy of this key to your friend. Anytime you have a message, you encrypt it using this key and then send that message to your friend, and then your friend also has that shared key and they can use it to decrypt the message. This is something like what friends might do in middle school to avoid teachers reading their notes. Public key encryption is a more common way of doing things today. With public key, the key is stored somewhere in some sort of authentication server. So if I were to send you a text message or something of that sort, the application would encrypt the message, and then when the application sends the message to you, the application will use its key to decrypt the message, and then you can see it. So cryptography is actually an ancient idea. The earliest instances of cryptography that have been recorded were sometime around 1900 BC. There was a set of hieroglyphics on the inside of a tomb in ancient Egypt. These messages were simple messages, but the scribe also etched advanced hieroglyphics into the message as well. Whenever you're reading it, it seems to not make much sense, so you just have to know which glyphs to ignore, and you can get the actual message. A little bit later, actually a lot later, at about 100 BC, this is when Julius Caesar himself came up with what is called the Caesar cipher. This one is incredibly easy. You just take the letters of your message and shift them forward 3 letters. And to decrypt it, you just shift back 3 letters. So A becomes D and J becomes M, so on and so forth. To get the message, you just go 3 backwards. Sometime in the 16th century, a Frenchman by the name of Vignère decided to create his own cipher as well. The way this one worked was by choosing a cipher word. This is usually a single word, easy to remember, and you would write out the message you wanted to encrypt, and then write your keyword above it, matching it letter for letter. You repeat the keyword over the entire message until you reach the end of the message. Once you're done, you'll have pairings of letters, and you take this pairing, plug it into the table that we have the picture of here, and you get your new letter. So repeat this over and over and you get your encrypted message. If someone else were to have your keyword, they could also use the table to decrypt your message. So during the wars, Germany developed a machine that uses random gears to continually encrypt messages. This would be famously dubbed the Enigma machine. The cogs on this machine had letters, and those letters would be randomly applied to the message, causing a random array of more encrypted letters. The recipient of this message would also have their own Enigma machine, and they could use that machine to unscramble the message as well. This machine was originally broken by a Polish mathematician named Marian Rejewski. I'm probably saying that completely improperly. The work that the mathematician did was also groundbreaking, but short-lived, because for the Second World War, the Germans had completely redesigned the Enigma machine using newer computing technologies, and this resulted in an even greater number of random possibilities for the message encryptions. So Enigma was a huge trouble for the Allied forces in World War II. Without the keys, the Axis powers were free to pass messages right under our noses. That was until Alan Turing showed up. Turing created a machine that he called the bomb, and this machine was able to run a massive amount of calculations every second. These calculations would run against the encrypted Nazi messages and eventually found the algorithm used by Enigma. Cracking the Enigma code was Turing's greatest achievement, and he is perhaps the most important figure in cryptography because of his work. He eventually went on to further the research on cryptography, and he published many papers on the subject, even going on to develop computers specifically made for this person. Now, a lot of you may remember there was actually a movie about Alan Turing's life starring Benedict Cumberbatch called The Imitation Game. I highly recommend watching this movie if you haven't yet. The presentation that I'm doing right now is not enough to go into the life of Turing, but his story is truly fascinating, and what he accomplished was truly amazing. His story is one that deserves to be heard by as many people as possible. So in today's time, we use cryptography nearly constantly. When we go to a website, our connections are encrypted, our data is encrypted, everything we do is scrambled. This is handled with authentication servers, as we talked about earlier, as well as protocols such as SSL and HTTPS. It's also possible for us to encrypt our entire hard drives in our computers. With just a few clicks, we can open our hard drive and apply an encryption to it, making it harder for anyone to get a peek inside. The influence our modern computers have had on cryptography is also quite massive. Back when Rajewski and Turing were cracking the Enigma, they were using old computers like the ENIAC that ran off of vacuum tubes and took up massive amounts of space. And today we have computers stronger than that in our pockets. We can compute faster, and with the faster computers we can handle larger algorithms. Larger algorithms, simply put, means more possibilities. So how does this relate to cybersecurity? Well, the whole meaning behind cryptography is security. If we have important information, we can shuffle it around to make it unknown to outside eyes. Encryption keeps your important information secure, and cybersecurity is all about that principle. Criminals would naturally take a liking to this concept. If you can conduct illegal activity and then hide the correspondence effectively, brilliant. Black hats can use cryptography to pass messages between each other, and without the key, it makes it way harder for the white hats to figure out the details of the messages. There was also a case that happened recently about the FBI versus Apple. There was a criminal who used his phone to conduct some sort of terrorist planning or some sort, and his phone was locked. The FBI couldn't get into his phone to access the data, and that phone could have had more information on it, but it was hidden behind the lock. So the lock also had a timeout feature that prevented a brute force entry method, so the FBI went after Apple to try to get a backdoor. So in this situation, the criminal used encryption to keep their phone locked and secure. Cryptography can also pertain to currency. There is a currency called Bitcoin that is used for online transactions and can disguise where money is coming from. This currency was very helpful in illegal online markets such as Silk Road. People were able to convert their real currency into Bitcoin and use the Bitcoins to buy illegal stuff. But there are still a few ways for the white hats to keep up, however. There are currently talks of ethical hacking becoming a thing. This would give permission for hackers to hack into a criminal's encrypted data and get whatever is inside. We do have to be very careful with this, however, because when it comes to forensics, integrity must be upheld. This will be an interesting topic to keep an eye out for going forward, however. We're also making technological advances in computing that will help a lot with cracking encryption, but we'll go over that in just a second. Also, as we saw in the case with Apple and the FBI, it may be possible to program some circumventions to bypass encryption. In the case with Apple, if we could program the phone to not shut down after the 10 attempts, a brute force entry method would have taken very little time. So the future of computing is actually quantum computing. This will make computing go way faster. Normally computers run in bits of ones and zeros, but quantum bits will not only be able to be 1 or 0, but they can be both. So this can increase computing power exponentially and allow an absurd amount of calculations in the same amount of time. When we come across an encrypted piece of information, quantum computing will let us run more algorithms against the encrypted piece, and we can, in theory, find the key faster. With the decryption as well also comes with encryption. With the power to run algorithms in a much higher volume, we can also create more complex ciphers. Quantum computing will make our current state of encryption fairly obsolete, but it will also usher in a new generation of encryption. And here are my references. I tried a different style of formatting with the references, hopefully making it a little bit easier to see my references and where they're placed, and hopefully make it a little bit easier to look into them a bit more. So with this presentation, I hope everyone has learned something, or at least got a better understanding on this important topic. Thank you everyone for listening, and take care.